here we were. I'm going to replay the best of, right? We had this. These are the types of problems that we're solving. Mapping problems between spaces, the space in which your data live and the space in which your problems live. Both of these will require separate consideration. Today, we will mostly talk about how to do the mapping. It'll be revealed to you. And then I give you an example of how to do this, setting up the problem, which says, well, this is really what you want to do. It establishes a notation, it establishes the relation. This is really the model. I try to be careful and distinguish the model from the instantiation of it, from the model parameters of it. So the model is linear. The model is quadratic in its linearity. Here, this is an example of how a quadratic function is specified that nevertheless linearly relates to the data. I haven't given you the solution yet. I'm going to get there today. And I certainly haven't given you the various variations of the solution. And so before I do that, I actually want to raise a few more questions that will make you appreciate the types of solutions that we'll get for this problem even more, okay? So maybe I'll add here just a note, no solution yet. So let me call this today here some more problem examples. And I told you this is not really technically earth science class, right? Or even a natural science class, although those fields of science have been at the basis of the development of so much of this material because the problems are so particular. It's not about it being an earth, it's about the nature of the problem. If you want a one-line motivation, which I've already used on you, it's that, well, the earth is a giant ball and we want to see inside. And so invariably, anything that we want to do is an indirect mapping. We are not engineers who can make an instrument and build the system from scratch. We are not physicists who will break down the problem to its smallest components. If we want to know what's inside the earth at 300 kilometers depth, we will never engineer that. We always must do direct inference. We will never directly probe it. And so that's shared with astronomy, cosmology, and geophysics. And to some, that makes it not even a real science because we can't really do an experiment. But we have been doing these thought experiments of, imagine there are many Earths and we could measure it an infinite amount of times. And so I'll just give you a very, very direct example that will make you appreciate this right away. Example 1. If I tell you a basic fact about the Earth, say, let m be the mass of the Earth, and let a be the radius of the Earth, and let I be the moment of inertia. I'd like you to note that I'm using the word moment, that we've used the word moment before, that we've defined moments as weighted, levered integrals. And then I said to you how the center of the mass is the first moment of the density distribution. The 0th moment is the total mass. The second moment is the moment of inertia. If none of this is familiar, you really shouldn't worry. Well, you should worry a little bit because we do live on Earth and we use moments all the time. But if it's not immediately familiar, you don't have to panic. So if I make a model now of the Earth that is, as you will know, demonstrably wrong, and that postulates let the Earth be a solid, homogeneous ball, okay? Tell me what's wrong with the Earth being a solid, homogeneous ball. Gut reaction to it.
The Earth is not completely spherical, and it's definitely for sure not homogeneous.
Okay, and so you're definitely picking at the edges by quibbling with the sphericity of it. That's a part in 300, okay? Your bigger quibbles are with homogeneity and solidity, presumably.
The Earth is not solid. The Earth also contains an atmosphere, and it has oceans
You drill a hole, then what happens?
You reach the core if you dig deep enough.
Okay, the core, do you define the core as the center of the Earth or some other ball inside of it? And what about the core?
It's molten?
That's what I want, okay? The Earth is not a solid ball because, for starters, it has a liquid iron outer core. Okay, that's just like it's a big thing, right? I also was vaguely hoping that you would say that if you drill a hole, then lava comes out, and then I would have to send you back to middle school. Okay, because when you drill a hole, lava does not come out. The Earth is not liquid in that sense. The rock isn't molten. You know, sometimes it's hot, and near the surface it will melt because of the lack of pressure. Okay. Still, if it were, and this was my model, I would say R bar is my mean density, all right? So if I then did a little bit of physics, I would write my constraints, I would write my model as follows. The mass of the Earth, integrate, would be this in terms of the density. And the moment of inertia, which is typically divided by the square of the radius, because then the ratios will effectively tell you how non-homogeneous the Earth is, but that's for another course. So the relation here is 8 pi 15 a to the third rho hat. And forgetting or borrowing for the moment, however we measure this, I'm going to write some numbers down, which I don't remember, and neither should you. 10 to the 24th in kilogram, 1.975, 10 to the 24th in kilogram. And, well, if you solve this problem, you just have to take it at face value, right? And so the first constraint here leads to a mean density of 5.5, 10 to the third kilograms per meter cube. That's meters cubed. And the second constraint leads to a density of 10 to the third kilograms per meter cube. That is a different number. Okay, so we all know that one thing is not equal to another one. There is no uncertainty on this thing, so, but there might be a way to reconcile it, but it's not the same thing. And you and I know that it's definitely wrong because simply the Earth is not a homogeneous ball. Okay? But what I want you to notice is that you've solved an inverse problem if you do this. And you solve the following inverse problem. The data is linearly related through a matrix equation to two unknown model parameters, which may mean physically the same thing, but because the model specifies them in a different way, they're not the same parameters. They are two parameters. And the elements of the G matrix, if you will, are this here. The mass is 4/3 pi 3 of the first density and has nothing to do with the other density. And the reduced moment of inertia is that 8/15 a to the cube, only talking to the second parameter with no relation or bearing on the first parameter, okay? And if that is my same as ever, D equals G times M dot times, then by doing it row by row, you really have obtained the solution by direct inversion of a square and diagonal matrix. And so my first model, this is MI for Roman I for 1, is simply the inversion of the data. Okay, it's a little bit hard to use the words properly here. I prefer to say this is an inversion for model parameters based on data You'll read papers, people say, I invert the data. I'm like, you're not really inverting the data. People say, I'll invert the model parameters. I'm like, that's also not what happens, right? So the definition is you're inversion of the model constraints, really. You're inverting them for the model parameters to obtain the model parameters. You're applying it to the data, whatever the use it in a sentence examples are. So the first solution to this simple inverse problem that has two equations, two constraints, and they do not have any crosstalk, which means no diagonal elements, is just literally the inversion of the data. Okay, well, I have room for model 2. And let's just give the Earth a core. See how far we get with that. And let's give the core a radius of C, where before the radius was A. And now we have two radii, namely A and C, still spherical. And I should tell you what the radius of the Earth was, 6,371 kilometers. I don't know almost any numbers related to the Earth, even though I am an Earth scientist doing the Earth all the time. I do know this number, okay? You should know that number. If you don't remember that, divide 40,000 divided by 2 pi and get the same thing. Don't ever look up how much this is in miles. It will just confuse you. You never need that. This, though, it's a handy thing. And I never remember C very well, but so having introduced it here, I'm reading it off my notes here, is 3485, which I remember as about halfway. Now, if you were an Earth scientist, you'd also say, well, hold on, there is also an inner core, and that's solid again. And I'm like, I'm not interested. I'm just going to go from one model that is clearly wrong because I should get the same result, really. I mean, I didn't talk about uncertainty. We haven't talked about uncertainty, but you can see that there's some issue with it. If only the fact that you cannot pick up a rock on the surface of the Earth that has a density of 5,500 kilograms per meter cubed. There are, that's extremely unlikely to find one in the field, right? You got to go dig the Earth to find rocks like that. So I'm going to do slightly more physics here. I'll just have two constraints. I'll have the mass and the reduced moment of inertia. And if I do a little bit more physics, which again is not the point here, so I'll just write it down here, you'll see that you get a different matrix. And I'm going to write just the important elements, taking out a factor here and there, just for you to see that previously it depended on A cubed. Let me just write it, and then I'll point to it. If you want to become an Earth scientist, or a planetary scientist, or a physicist, and you don't already know how this plays out, then you should do this at home. I'm factoring the 4/3 pi because that's just cumbersome. And I'll write the dot products where I need to. And now I don't have two models for the same average density of the Earth, but now I have two densities, one for the core and one for the rest of it. So I'll give this rho 1, and I'll give this rho 2. And so now what I want to say is, well, obviously this looks exactly the same in its linearity. It's a completely different model. But again, the solution is completely given by this here, because this is a square matrix that when I attempt to invert it, doesn't give me any sort of headaches of any kind. And so I'll just write solution 2, write a problem formulation 2, and I'll say, well, fine, I can't give the same name to the same thing. So I'll call this upper G 1 or 2. So G1 has been inverted to give me model 1, and G2 is going to be inverted to give me model 2. Same data, different model, different G matrix, different sensitivity matrix. So I have a different solution. And I suppose I should write what the solution is. So you do this, and you see you could do this by hand, right? You do not have to be a mathematician to invert the 2x2 matrix. You'll just write A, B, C, D times which E, F, G, H equals 1, 0, 0, 1, and you chug through. This is not at all hard. And you could do it, in other words, in closed form analytically on a piece of paper in a minute. And well, just for earth science credit here, I got two solutions, rho 1 to rho 2, and they are something like 12, 10 to the third, all in standard units, and 4, 15, 10 to the third kilograms. Now, if you're a geologist, you're getting to be somewhat more excited because, yeah, you know, the density at the surface, about 4. That's still too high, but, you know, we're getting there. And the density inside of the Earth of that core, which we don't know is liquid or solid at this point, you know, is definitely higher. And if it was all iron, then we also would be almost getting there. We haven't talked about uncertainty again. We haven't talked about anything else. And what you have to understand is that both these two solutions are exact solutions, right? They fit the data exactly. They are both, however, wrong. This is a very important part. It is not because you fit your data exactly that you have achieved the truth. No, then you have achieved exact data fit. We know that the first one's wrong because two things that supposedly describe the same thing can't exactly fit the data and both be different. And we know the second one's wrong. No, we don't really know how wrong the second one is, but we would know it if we picked up some rocks and did some, you know, lab experiments and so on. But the fit to the data here doesn't tell us that. This is a very, very important point. Right, like this example, which, by the way, is coming from that book that I've been recommending also on the outside, which is by Gubbins. I wrote it down last week. G-U-B-B-I-N-S, Dave, to his friends. All right, well, if you're a primitive earth scientist, and let's say 1700s type of earth scientist, you know, like maybe slightly after Newton, you'd know all this. You'd have to have a notion of, well, Newton would have had to exist, and Cavendish would have had to be born and raised and done this famous experiment. But it's 200 years ago, people would know this, and they would know it's wrong. So let me try a third model, model 3. Okay. And then I was like, well, how about I try to satisfy both constraints at the same time? So I'll write my same data. I'll still want a single Earth, so an Earth like in Model 1 again, but this time I'm saying, look, whatever it is, I know the mass is 4/3 a cubed, and I know the reduced moment of inertia is 8/15 pi a cubed, and whatever it is, I am just going to want to solve for a single density, not two potentially different densities, but one density that somehow tries to satisfy these data at the same time, okay? So tell me something that comes to mind when you see a problem like this. How would you solve it?
So you're trying to just find one density instead of two.
Yes.
So my first thought, I'm not super familiar with matrices, so I don't really know how to solve them, but I guess like I would think, couldn't you just average your two densities, even though that would give you still only a very rough estimate of the answer?
Ah, that's an interesting suggestion, which I had not thought about. So you're saying just go back to Model 1 and take the average.
Yeah.
Is what you're saying. Okay.
I'm sure it would be different, but
yeah. I'm gonna put it here as a note here. We should explore this. Could we go back to Model 1 and average the results? The answer is yes, we can, but the question is, what would that imply? Okay. Yes. Even though I hadn't thought of doing it this way right now with you, I think that what you said is very important, and that is, well, what thereby have you admitted? Because when I did Model 1, I'm saying, well, I satisfy my data. This is what it is, people. And so if you're not going to say, well, actually, no, I have two results, I'm going to average, you have given up on fitting the data exactly. You have admitted that your data may be wrong, that the data may be in error. I don't want to talk about the truth, right? I wanted you to not think of error in terms of, oh, but it's wrong, the Earth is not of a certain density. No, this is really the fundamental thing here that one has been admitting here is that the data are imperfect. So your solution of taking the data and averaging, you have two data points and you average the result, and then you're sort of, if you back calculate it, then you're saying, well, but that actually is not reconciling the data individual. And then you're saying, well, tough luck, the data probably weren't perfect. And that's how you bring uncertainty into it. But I think that is fundamental, what you just said, even though that's not what I was going to do here. And in fact, let me hold off, because I think it's a good thing to do. So as we have admitted this, okay, we really need to go back to our fundamental description of our data problem that is here, right? That the data is given by, and I'm going to rewrite that, right? Never forget that our model really was, there is data, there is, now I've been doing the unknowns in red, I suppose. Actually, my data are now black today. My model is blue. My model parameters are red. And we're just never forgetting that there is a truth here, but that there is a noise component to it. That's a way of encapsulating data imperfection. And as soon as you've admitted that, you're open to saying, sure, I'm not fitting the data perfectly, but you know what? They were not good enough to begin with. This is supposed to be the truth. And this is contamination, noise, imperfection. I think I used the words early on in the lectures that geophysics and this sort of planetary physics is really about gross, inaccurate, inconsistent problems. So those are sort of words that come up. Gross comes up in this way, not quite in the sense of ugly, but in the fact that you have to take things from a distance and average things out. And I'm not saying it right now, so I'm not going to use the word here, but inaccuracies, imperfections, noisiness, all of those terms come up, okay? So going back though then to the earliest worked example, you see that the problem that model 3 is exactly the same. You have only two model parameters, but you have two data constraints, and you've already admitted that they don't have to be fit perfectly. And then, fine, that's the way it is, right? So now your objective is not like in model 1 to find a solution, or like in model 2 to find a solution and calculate something exactly, but to say how much leeway you're accepting, how much of this inaccuracy you want to take inside of the problem. Now, only do we define a measure of success. Let me just go to the familiar notation that I introduced a while back to say, how about any m hat, okay? So this model G, it may be wrong, but it's your assumption, it's your idea of the world. And given that idea, then this m here is the vector of true model parameters, right? If Newton's right, then that's the gravitational acceleration. If the Earth is a homogeneous ball, that's the density, okay? So now here with the hat on it, we're having an estimate, okay? Whatever happens, however we solve it, and I'm still not there, but so we will try to find an estimate for the truth, and we measure our success by running the implication backwards and saying, well, look, G dot M hat is just saying, well, under the idea of the model, the hypothesis of the Earth being flat or Newton being right, This is making a prediction. Another word for making a prediction is that now suddenly you've created a data vector that gets a hat on it because you've made a data prediction, right? And you're always going to do this here. Any inverse problem, any code you write, you're always going to have the construction of the model matrix, G. You're always going to collect the data in the vector. You're always going to find a way to make a model estimate, and then you're always going to retro predict the data from it. And now I would say, let's call it error or residual, is of course going to be the difference between the prediction and the observed data. So whatever D was, I'll now compare it with my solution, however derived, and that's your error or residual. And now you need to reach back to everything that we discussed before, because E is a residual vector, and we need to start thinking about this statistically. We need to start thinking about what variance and bias are going to be. But even before that, we need a way to sum things up. And I'll just introduce now the following. I'll say, well, one example of the measure of success, and clearly the most popular example, which is good often, popular for sure, is that you're saying, well, look, I want this to be small, I want to minimize it, but I need to specify what of E I want to minimize, and I want to minimize the sum of squares of it, and in my matrix notation, I want to just call that E dot E, and I want to call this with a new notation the true norm of the error. It's 2 because you're forming products, and this is the sum of products of the element. And it's a 2 up there because when you think it through, that's really the square of the length of the vector if you're doing Euclidean geometry. And this we're also often calling phi. Okay, so if you, now everything's boxed, it seems like everything's important here. If you say, thank you for this inverse problem, and try to find a solution, the solution is a model vector that will make a prediction. So my measure of success is that the solution produces an error vector that when I mean square it, forget the 1 over n, you know, it's a factor that drops out if you minimize. So in this sense, in this squared sense here, you want this to be minimal. And well, that leads back to my definition of my estimate. I'm going to start renumbering here. So I can say, look, the first way by which I'll be solving these inverse problems, it's getting complicated here, but this is the renumbering, okay, because then there'll be a second way. No longer big I, or Roman numerals, but you know, I'm into like an actual definition here. We're now going to say, okay, the first solution that I'll make of this class of inverse problems, I'll just say, give me the argmin, those arguments that for all ranges, for all possible values, for wherever this space leads you to, for all of those, I have a phi, I have a functional in terms of the model parameters, because the error depends on the model parameters, phi depends on the model parameters, and so my true definition is that my solution is the model vector that in the space of possible model vectors minimizes a mean squared error in this sense. So it's wrong to write m as the minimum of 5 because the minimum of 5 is a number that says how big your error is. That doesn't give you the data. That doesn't give you the model. So m is the arguments that minimize over this space the root mean square error in this sense. It's all on the page. Okay, so now I told you what I want, but I haven't told you how to find it. And before I go on, I'll still want to make 2 or 3 more considerations. Always have in the back of your minds, and it will come back, right? When we talk about D, we talk about a model G, we talk about an unknown vector M, we talk about an additive noise contamination. I want you to be mindful of the statistical interpretation, okay? What's important here? First of all, this is additive noise. That implies a linearity that we're going to exploit. Obviously, this product is a linear operator. And if I say mind the statistic, then let's go with the following here. Let's stipulate that n, this noise vector, it's going to be a random variable. Okay? And nobody here needs to talk about the distribution yet, but realizing that it is a random variable, we know it has a distribution. There is a PDF, and it's going to have an expectation, and it's going to have a variance, and it's going to have all sorts of things. And I want to make the following minimal assumptions about this thing for you to keep in the back of your heads, that the expectation of the noise vector is the 0 vector, right? Make a good measurement. Don't be off all the time. And if you are off, correct for it, right? A bias in measurement, a systematic thing, well, try to shift things out. And this is as easily said as done. This is not a massive restriction. This is a very useful restriction. Well, it's a very mild restriction here. And it underlines what follows, and that those are the conditions under which whatever follows is true. And therefore, if whatever follows isn't true, then this is the thing to start revisiting. And if I call that thing there the noise, which I have, then I want to call that the signal, right? So let's call this signal, and let's give it a letter, S. And I'm writing it this way to make it maximally useful and connecting to the things that we wrote earlier, much earlier. But remember where we talked about signal noise in general? Here, okay? There is a reason this is full of boxes and excellent handwriting, I may say so myself, where all the assessment of what you know is going to be with how close it is to the truth on average, what the variance is, what the residual, and so on. And there, look, there's our mean square error again. So we're going to bring this back here. I'm making one more assumption, which is going to come in handy later, that the covariance between the signal and the noise is going to be a 0 matrix. And now I'm going to look in my notes for where I last wrote a notation like this, and I may have stuck in a comma or a transpose, but it certainly came around this time where I gave you that error propagation formula, right? There we are. See this one? Like the covariance of something. This was the covariance of X with itself, which is really the covariance of X with itself. And so this notation what we were then using. And so that X here, that's the same one. And so if we think of S as a column vector and N as a column vector, then I really better put the transpose on here. Okay, clarification, the noise is 0 in expectation, mild condition, so the best working environment. And the covariance of signal and noise is non-existent. Okay, so that's another way of having a good measure. So that's in the back of our minds, and in the back of your minds now needs to be the fact that whatever we're going to come out with, we're going to want to know about the signal. And since G doesn't change, really we're going to be able to make inferential statements about how close our model estimate is on average from the truth, which will be the bias, which obviously we want to keep low. We're going to talk about the variance of the model estimate, the model estimation variance, because again, we want this to be small. The mean squared distance of models made in this way, of data given in this way, needs to be on average small. And that is consistent, will be soon, with our initial requirement that says here, you know what? I have already defined my error of individual term as d minus gm, and my mean squared error is an estimate for the average contribution of variance and bias. And so that's what I'll be minimizing. So this is all totally consistent and making as much sense as I can make out of it. And then these two are the conditions that we postulate from the beginning with which we will retroactively validate it. So now to the solution. All right. Well, how does a person minimize a thing dependent on parameters? So what's the next thing that we're going to do to minimize phi? We have a function phi of parameters n. What operation will I need to do to find the minimum of that function? Very generally.
To find the minimum of the function?
Yes.
To take the derivative?
Yes. To minimize, differentiate. Okay, well, I'm going to just write that. I will apply the derivatives in every one of the little m's. If this notation is weird, it is also wonderful. So the m gradient needs to be 0. That's what I want. If the function is not having a derivative in any of its coordinates, which are given by the individual model parameters, as many as there may be. So again, I'm thinking of a discrete system. I can just count them. Then it's going to have reached not necessarily a minimum, but at least a stationary point. Okay. It may well be that you have reached a maximum, in which case you are not getting the right thing. And then you may need to check its second derivative to figure out if it was a minimum or a maximum. But you cannot get around the condition that we need to differentiate phi. And phi, if you recall, but I'll write it here because it's on the previous sheet, and I'll write it beautifully as with all the dots. Phi is the dot product of the difference of the model vector multiplied in a dot product with the parameter vector. If you want to write this out in components, please be my guest. Stick in an I for every rank index. So for a vector, you have 1 index. For a matrix, you have 2. And stick in a letter for all of them. If you see a dot product, make the adjacent letters the same. And when you see a repeated index, you sum. Those are the rules of dot products. Okay, fine. Whatever that means. Then you have a bunch of sums and indices. And if you're more happy to work in that realm, you know, do that. Here, I just want to read this left to right, and I want to come up with the result that makes sense. So I want to use a product rule. I want to be mindful of the transpose. The bottom line is I get out GTG times D minus GM needing to be 0. And so clearly GTD must be equal to GT dot G dot M. And immediately that leads to our first solution, which I've numbered 1, remember? Now that's a model estimate. And I put the hat in here to say, well, that's that one that does the minimizing. And that's given by the formula that you should never forget. GTG inverse times GTD. All right. I don't remember numbers, and I also don't remember names much, and I don't remember mathematical formulas, but this one I do remember. That is the standard overdetermined least squares regression, ordinary least squares regression. What is least? Well, the least is phi. What is phi? It's a sum of squares. That's where the least squares comes in. It's ordinary because, you know, if I could write in 10 minutes, surely it's not special. And it's regression for an interesting historical footnote that I will spare you now. but in which there are some unlikely heroes of the Romantic statistical era that I will give you another time. I'm going to give this whole thing a name because this is another. Here's another thing I want you to see here. I want you to see that we have defined a type of a solution, which I'm going to start giving a name, g to the negative g, which is some really hokey notation of what's called a generalized inverse. Okay. Model 3 for the Earth, g was a row vector. That's not a matrix. Nobody can invert that. But you can generally invert it, generalizedly invert it. You can multiply by its transpose, then that is squared, then you can invert it, then you can multiply by transpose again, and then you can multiply by the data. That should be possible. Nobody says that's right, recommendable, even doable, but you can write it down and you should try it. And that's the type of solution that we got. If you do that and you try it and it works, more about when it may not even work later, you know that you've done the least square solution. And what I want you to know about this operator is, well, what is it, right? It's the design of the sensitivity matrix, squared, inverted, and multiplied by its own transpose. So this is an operator. Even more an operator if I give the last dot, okay? So I want you to see that the solution to this problem is given by applying this matrix to the data, again, as a linear operator. So ordinary least squares regression is it's about finding for your specific problem, first of all, how the data constraints are playing out, which means fill your G, and then it constructs its generalized inverse, which is again a linear operator. And well, you want to see that it is a left inverse of G. It's not the inverse of G because it had no inverse, but it is the left inverse of G because when multiplied by G, of course you have the inverse of something times itself. That gives you the identity matrix, but only when coming from the left. Okay, I'm going to follow this implication. Right? The arrow comes through, also goes through here. We need both of them, right? I would just want to write out again what we've just done. And notice that, well, look, I'm applying, maybe I'll just write it out. I'm just copying it. G to G inverse times GT, right? Times D. Oh, well, what was D? Aha, well, D was G times M, the truth, plus noise. That was here at the top. Just putting it in there. Now my statistics come back to pleasantly haunt me. And my stipulations come back that if I say, well, if I do it this way, then the expectation of my estimate is the expectation of the thing to the right. But you know the expectation has no bearing on the G's because, you know, that's not a random variable, that's a model specification. It erases the expectation of the N, which is the noise, and I've just said that the noise is on average 0, which means that the expectation of my thusly constructed solution vector is equal to the truth. What does that imply? How do you then characterize this sort of a solution when in expectation the thing you want is equal to the truth? I need one word to fill the sentence with. The model estimate is the statistical characterization of it.
So the model estimate is unbiased.
Okay, say it again. Let it ring in your ears. If the expectation of the thing is equal to what you want to know, it's unbiased. And if it is unbiased, that's a good thing. Okay, we haven't talked about the variance of the error. We haven't talked about the mean squared properties of the model. We've just done the mean square property of the data. I wanted to say two more things, really just words. I'm highlighting this GT transpose G, and I'm going to give that a name just because it's going to come back. I'll call that R or RM, which is the model resolution matrix. It really means that, look, whatever that comes out as, it's a linear operator when applied to the truth. And so if you want to see how your truth gets muddled, convolved, if the case may be, to forming your estimate, R is going to be the way that tells you what that is. That's the model resolution matrix, but I'll write it later. And Menke talks about that a lot. Here I've just said the model estimate isn't biased because an average is close to the truth. I'm making a couple points here at the end. I know the time is up, but it's a linear operator, but I've already taught you how to do error propagation. So if I give you a data covariance and I say I've made this error, then you can make me a model covariance, and then you can talk about what the mean square error or the variance of the model are. Those are things that are now immediately accessible to us. And finally, I want to make one point and ask you all, why is today an especially good day to talk about the generalized inverse? It's related to the news. If it doesn't immediately ring a bell, does it ring anyone's bell immediately? Did you read the news today? Any of it?
Does it have to do with the Nobel Prizes being awarded today?
Yes. Did you click on who won the Nobel Prize today?
I know Roger Penrose won.
What is one of the things that Roger Penrose did that he didn't get the Nobel Prize for?
I know he worked with determining singularities in black holes, but I don't know how that's related.
Well, his name's going to come back up, but Penrose is associated with a generalized inverse, which is almost a proof to that rule, whose name I can't remember, but he's remembered for this and is very distinctive because we're going to come back to this. But he's like the third to come up with it, and yet he's the name that we remember. You're going to hear the name Moore-Penrose, and as I was Googling it today, there was actually a geodesist who did that in between them, and so there really should be a Moore-Bjerhammer-Penrose, but that's taking us too far. But so I clicked on Penrose today, in the news, and it's like, the many things he did, there's a real physics, but he was really a mathematical physicist, and very immediately in his bio comes out the fact that he did things related to the generalized inverse. And some 10 years ago, he gave a talk at Princeton, which was, I think, one of the worst delivered, very interesting talks that I've ever seen. But he didn't talk about any of that or any of the black hole stuff, but talked about the tiling, which is a story for another day. So I think we're done here. We've brought the overdetermined inverse to a practical form that tells you what it is that we're actually doing. I'll talk about covariance next of the model. I talk about other things. I'll talk about when it doesn't work. I'll basically keep talking until you tell me to stop. Oh, I didn't point out my t-shirt.